Hi everyone! In this video, we're going to state and prove the Azuma-Hoeffding bound. This is a really useful tail bound. It's kind of like a Chernoff bound, and it's proved in a similar way, but it works on sums of random variables that may be dependent. In particular, it works on sums of random variables that form a martingale. So here's the statement of the Azuma-Hoeffding bound. Theorem. Let z sub t be a martingale with respect to x sub t, and suppose that there are some constants, c1 ... up to cn, so that for all I between 1 and n, the absolute value of zi minus zi minus 1 is bounded by ci, with probability 1. Then, the conclusion of the theorem says that for any lambda greater than 0, the probability that zn deviates from z0 by more than lambda is bounded above by 2 times e to the minus lambda squared divided by 2 times the sum of the ci squareds. This might seem a bit abstract, so let's put it in a context that we're already familiar with. In particular, let's compare this to a Chernoff bound. Suppose that x0, x1, ... up to xn are the outcomes of n random coin flips, so 0 with probability 1/2 and 1 with probability 1/2. Now let's define z sub t to be the expectation of the sum over I of xi conditioned on x0 up to xt. So this is the Doob martingale where the quantity that we care about is this sum, the sum over I of xi. Now this is a situation that we've studied before in the context of Chernoff bounds. I have a bunch of independent random variables and I care about their sum. So just to see what Azuma says in this case, let's try to apply it. In order to apply the Azuma-Hoeffding inequality, we need to bound these differences zi minus zi minus 1 for all I. So let's do that. Zi minus zi minus 1. So by definition, this is equal to the difference of zi, that's the expectation of the sum over j of x sub j conditioned on x0 up to xi, minus zi minus 1, it's the same thing, except the conditioning only goes up to xi minus 1. Now observe that no matter what x0 through xi minus 1 are, no matter what these values are, they're going to be the same in this sum and in this sum, because I'm conditioning on those random variables. So that means that what's left is the expectation of x sub I conditioned on x sub I minus the expectation of x sub I, no conditioning. But this, the expectation of x sub I conditioned on x sub I, is just a fancy way of saying x sub I. And this is just equal to 1/2. So this is equal to x sub I minus 1/2. And no matter what happens, this is going to be 1/2. It's either going to be 1 minus 1/2 or the absolute value 0 minus 1/2. And that holds for all I. So now let's apply the Azuma-Hoeffding inequality, which I've written up here. So it says that the probability that zn minus z0, I'll fill that in a second, is greater than or equal to lambda, is less than or equal to 2 times exp of minus lambda squared divided by 2 sum over I ci squared. So now what goes here? So zn is by definition the expectation of the sum of the xi's all the way up to n conditioned on all of the xi's all the way up to n. Another way of saying that is this is just the sum of all of the xi's all the way up to n. And then what is z0? Well, by definition, that's just the expectation of this sum, and there's nothing that I'm conditioning on. Sorry, I should have had these be 1 indexed here, so let's get rid of that guy and make this 1 indexed, so then z0 can actually just be this expectation without conditioning on anything. Sorry about that. So with that change, this is just the expectation of the sum. And now this looks like the sort of thing that a Chernoff bound also bounds. So let's see how what we get here compares to the Chernoff bound. So in this bound here, each of these CI's is equal to a half. That's what we got there. So this is going to be equal to 2 times exp of minus 2 lambda squared divided by n, replacing each CI with 1/2. And this is basically exactly the inverse exponential sort of behavior we'd expect from a Chernoff bound. So what we see here is that the Azuma-Hoeffding inequality will recover a Chernoff bound in situations where it applies. However, as we might see in some applications later on, the Azuma-Hoeffding inequality is more general, and we can apply it in cases when we wouldn't be able to apply a normal Chernoff bound. For the rest of this video, we're going to prove the Azuma-Hoeffding inequality. To prove it, we're going to first prove this lemma. The lemma says that for any random variable y, that is with probability 1 bounded inside some interval minus c to c, and that has mean 0, we have that for any t, the expectation of e to the ty is bounded above by e to the t squared c squared divided by 2. So let's prove this lemma. I wrote the lemma up here. First, I claim that it's enough to prove the lemma for c equals 1. Indeed, suppose that y is contained in minus cc, as in the statement up here. And now let's define y prime to be equal to 1 over c times y. Then y prime lives in minus 1 to 1 with probability 1. And so if we could prove this statement just for c equals 1, we could apply it to y prime, and we conclude that the expected value of e to the ty prime is at most e to the t squared over 2 for all t. Now plugging in the definition of y prime, that means that e to the t y over c, the expectation of that, is at most e to the t squared over 2. And now changing variables, let's say that s can be equal to t over c, I get that for all s, e to the sy is less than or equal to e to the s squared c divided by 2 for all s. And this, at least changing the name of s to t, recovers this lemma. Therefore, it's enough to prove it for c equals 1. So for the rest of the proof, let's just assume that c equals 1. So I've replaced c with 1 up here in the corner. Okay, so first I claim that for any y between minus 1 and 1, some random variable, the expectation of e to the ty is bounded above by this, e to the minus t plus e to the t all divided by 2. To see why, let's first observe that for all y in minus 1, 1, e to the ty is at most 1 minus y over 2 times e to the minus t plus 1 plus y over 2 times e to the t. And this just follows by convexity of the function e to the ty. If we were to draw a quick picture to see why this is true, suppose that this is e to the ty, and here's 1, and here's minus 1. So this is e to the t, this is e to the minus t, and if I join them with a straight line and I look at some y here, this point has value e to the ty, while this point, which is notably above it, has value this thing, 1 minus y over 2 e to the minus t plus 1 plus y over 2 e to the t, just because it's interpolating on a straight line between those two values. Okay, so given that this holds for any little y, we have that the expectation of e to the t capital Y, this random variable capital Y, is at most the expectation of 1 minus capital Y divided by 2 times e to the minus t plus 1 plus capital Y divided by 2 times e to the t. But now by linearity of expectation, this expectation can come in and work on that y and also on this y, and remember that the expected value of y is 0. So this is just equal to e to the minus t plus e to the t divided by 2, and that proves the claim. Check. Okay, now that we have this claim, it's Taylor expansion time. Woohoo! We can write e to the minus t plus e to the t divided by 2. This is equal to 1/2 times 1 plus t squared over 2 plus t cubed over 3 factorial plus ... plus 1 minus t plus t squared over 2 minus t cubed over 3 factorial plus ... That's just taking the Taylor expansions of these things. Now, half of these terms conveniently cancel with each other, and what we're left with is 1 plus t squared over 2 plus t to the 4th divided by 4 factorial plus t to the 6th divided by 6 factorial, and so on. On the other hand, let's consider e to the t squared over 2. This is the thing that we eventually want to have on the right-hand side. The Taylor expansion of this thing turns out to be the sum, for all j greater than or equal to 0, of x squared times j divided by 2 to the j times j factorial. You could just trust me on that one. So writing this out, this is 1 plus t squared over 2 plus t to the 4th divided by 4 times 2 plus t to the 6th divided by 2 cubed times 3 factorial plus ... And now we can compare these two things term by term. Actually, to make it easier, I'm going to move this so it's more lined up. There we go. And we can see that these two terms are equal, these two terms are equal. For these two terms, this one is bigger. For these two terms, this one is bigger. And you can check that always we can line up these terms exactly, and this one's going to be bigger. So what that means is that this expression here is bigger than that expression there. Or in other words, we can amend our claim up here to say that this is less than or equal to e to the t squared over 2. But that's great, because that's exactly what we wanted to show. So now we've proved this lemma. Check. We know that for any such y in the interval minus c to c, the expectation of e to the ty is at most e to the t squared c squared divided by 2. Okay, why did we prove that lemma? Remember, we were supposedly proving the Azuma-Hoeffding bound, which was this theorem that we saw before. So let's use our lemma, which I wrote here, to prove the theorem, which I've copied here. Actually, I'm just going to do one side of it. I'm just going to bound the probability that zn minus z naught is greater than or equal to lambda. If you notice, the theorem actually has some absolute values here, so to do it, I really should do both directions, the probability that this is greater than or equal to lambda, and also the other way around with xn and zn reversed, but I'm just going to do this one, and the other direction is basically the same. Okay, so this probability is equal to the probability that e to the t zn minus z naught is greater than or equal to e to the t lambda, and using Markov's inequality, this is at most the expectation of e to the t times zn minus z naught times e to the minus t lambda for all t greater than 0. So this is our standard Chernoff bound trick that we've already used when we proved Chernoff bounds. So we're exponentiating and then applying Markov's inequality. So now we basically just want to bound this thing. We have that the expected value of e to the t zn minus z naught is equal to the expectation of e to the t zn minus 1 plus zn minus 1 minus z naught. Here I've just subtracted zn minus 1 and added it again, so I haven't changed anything. And now I'm going to do some funny stuff with some expectations and some conditioning. So I'm going to write this whole thing as equal to the expectation of this thing conditioned on x1 up to xn minus 1, and then we end that outer expectation. So why is this true? Why am I just allowed to go around conditioning on things? It's because I then conditioned on this, but then slapped the whole thing inside some other expectation. So this outer expectation is basically going to integrate away this stuff. But now, notice that e to the this stuff is actually a constant, given that I'm conditioning on all of this. So that means that I can pull it out of this expectation. So this is equal to the expectation of e to the t zn minus 1 minus z naught times the expectation of e to the t zn minus 1 conditioned on x1 up to xn minus 1. But now consider what happens if I call this thing y. Here I'm mirroring the notation from the lemma. By the assumption in the Azuma-Hoeffding theorem, zn minus zi minus 1 is at most c sub n. So that means I can apply this lemma. I just noticed that I accidentally copied and pasted the version with 1, so I just replaced it with the c's that we're supposed to have. So I can apply this lemma where this c is equal to c sub n, and this y is equal to zn minus 1. And when we do that, we see that this whole thing is at most the expectation of e to the t zn minus 1 minus z naught times e to the t squared c sub n squared divided by 2. Now this is a constant, so I can pull it out of that expectation. And this is equal to e to the t squared cn squared divided by 2 times the expected value of e to the t zn minus 1 minus z naught. Okay, so we've made progress. What have we done? We started with this expression that we wanted to bound, the expected value of e to the t times zn minus z naught, and we've bounded it by something that we pulled out times the same expression but with a zn minus 1 instead of a zn. So the basic idea here is we're just going to repeat this. So here I've just copied over what we got on the previous slide. And if we repeat this logic, ... we're going to get that eventually this is less than or equal to e to the t squared cn squared divided by 2 times e to the t squared cn minus 1 squared divided by 2 times ... all the way down to e to the t squared times c1 squared divided by 2. And this whole thing is equal to exp of t squared times the sum over I of ci squared divided by 2. So recall from before, from our exponentiate and use Markov trick, we had that the probability that zn minus z naught being greater than or equal to lambda was at most e to the minus t lambda times the expectation of e to the t zn minus z naught. That was the whole reason we wanted to bound this in the first place. So now plugging in this bound that we just got, this whole thing is less than or equal to exp of t squared sum over I ci squared divided by 2 minus t times lambda. Now, remember, we get to choose t to be whatever we want as long as it's greater than 0. So let's choose t to be equal to lambda divided by the sum over I of ci squared. And we get the upper tail, we get this one direction. To get the lower tail, it's a pretty similar argument. Okay, so that proves this theorem. Check. Later, perhaps in class and or on the homework, we might see a few ways to apply the Azuma-Hoeffding bound. But for now, that's it for this video. Thanks for watching.